Hi, and thank you for joining this session. We're going to be reviewing ozone installations specifically in the United States and looking to see if review of their data provides any insight into industry trends and designs. My name is Justin Bennett. I'm the Director of Engineering and Operations at Mazzei Injector Company. I'd also like to take this time to thank the IOA group for allowing us to have this platform to collaborate and present ideas on. It's obviously been a very difficult time with the pandemic. It would have been very easy to just cancel this conference, but they put a lot of work and effort into providing us with this platform, and I'd like to tell them thank you for providing us with this. So first, we're going to take a look at ozone's history in the United States. Ozone was first used in the United States in 1908. However, between 1908 and into the 80s, it did not get general acceptance or adoption into water treatment plants as a technology of choice. However, in the mid 80s, the use of ozone started to really increase. And this actually coincides with the Safe Drinking Water Act's amendments of 1986. As of 2020, there have been over 500 installations, and the bulk of those occurring within the last 3 decades. That's not necessarily 500 unique installations. Some of those are plant upgrades, maybe changing over from an air-fed to an oxygen-fed system, or bringing on more ozone generators to increase their pounds per day, to increase their treatment capacity. But there have been 500 projects of some sort within this time frame, with the vast majority of them occurring within the last 3 to 4 decades. Taking a look here, you can see the ozone installations by year. We're only going back to 1940 on this scale, but you can see just very sporadic. And then as we work our way into the 80s, we're starting to see year after year some new installations coming online. And then as we get into the 90s, it really just explodes, where we're getting, over a dozen, 15, over 20 installations occurring on a yearly basis there. And you can see there in 2020, another good year with a lot of installations that have come online. 2021, 2022, there at the end. Those are some forecasts. Obviously, we're still in 2021. 2022 would definitely be a forecast. So that's just starting to capture some data from plants that we know, and including those. And so I'm certain those numbers will climb as we complete those years and more plants come online. But obviously, within the last 30 years, there's been quite an adoption of this technology. So we've limited our review then to from 1990 to present, because that's really where the bulk of the data lies. Yeah, we could maybe work our way back into the 80s. Prior to the 80s, there's really no point because there's not any data available to gather from there. But the vast majority of that data is from 1990 to the present. So that's what we focused our research on. So the first thing that we wanted to take a look at that we thought might be interesting was looking at the plant flow in million gallons per day and the ozone production in pounds per day. And we were curious to see if maybe early on, some of the smaller plants, being maybe a little bit more flexible and nimble, adopted the technology, and as more and more of those plants came online, the bigger plants followed suit, or maybe even vice versa. As the bigger plants were able to bring in that technology, the smaller plants saw what they did and how they did it, and they followed suit. However, what you can see here is there's actually no significant trend when it comes to plant flow. The larger plants, which we defined as greater than 200 mgd, are sporadically dispersed, and I say sporadically, you might even say evenly dispersed throughout this timeline. Where we have in the early 90s a large plant that came online at 600 mgd, and then another in the 96, 97, again another 600 mgd plant in approximately 2003. Now the gray line here represents the year. The blue columns represents the plant flow in MGD. So you can see that not really one size plant began the trend, but together they were both doing it. And what we define as a small medium plant being less than 100 MGD, those are consistent. Obviously, there's many more of those size plants available. And so those are the more year after year consistent plants that are coming online. But small, medium, large were all adopting the technology at the same time. Not really surprising, but the production of ozone kind of correlates with the size of the plant. more water flowing through a plant, the more ozone would need to be produced in order to treat that water. And so this graph here itself pretty much mimics the last one. So again, that big plant in the early 90s, you can see that first spike. That other, next big plant that came on in the 2005 area, and then another one in 2010. You can see the spikes there. So more water being treated, more ozone needed being produced. Um, the columns represent pounds per day of ozone being produced at each specific water plant. So again, not any trend that we can really see here. Large ozone production is sporadic with time, basically lines up with the plant flow. Ozone production less than 5,000 pounds per day is definitely the most common size. Probably could even say uh, smaller than that, maybe down to 2,500 pounds per day is the real year after year after year installations, with some of the bigger plants being spread in there. But again, no trend there in relations to which size or type of plant was the early adopters. If we take a look, though, at the cumulative ozone production by year, and so in this case, the blue line is the year, and then the orange is the cumulative production of ozone year after year, we see there's a nice steady growth of the ozone technology in the U.S. Where from 1990 to 2000, there's a nice steady growth. Slope increases there between 2000 to approximately 2005. Then you had that spike up that coincided with the large plant that came online, and then back to the stable growth again. Again, another spike there in about 2010. And then from 2010 to current 2020, we've had a stable growth rate that does not look to be slowing down. So definitely have not reached a maturity in this market at this point. There are more plants that can be utilizing this technology, that can be adopting ozone in. And so we look forward to the continued growth in this market in the United States. One of the other interesting factors we want to take a look at was the percent by weight of ozone concentration year after year. And now this starts to show some of the data gaps that are present in this data. So you can see there, the first data set we actually got was in 2003. So much more limited data, not quite as much as you can tell from this, but there are some things we can identify. So definitely the most common design point, at least from 2003 to current, is a 10% by weight concentration. Here recently, we're starting to see a little bit higher concentration. We're seeing some more installations coming in at 12%. So that's at least starting to show up with as much frequency as the 10% by weight does. But one of the things that's very interesting is we are aware of generator technology that allows for 14%. In fact, we have one point here in about 2016, 2017 at about 14% by weight. Generators that are able to run at this higher concentration. In fact, some generators that are able to run at higher than that, 16, 18, 20% by weight. But we're not seeing those utilized in the designs and in the plants that are bringing on ozone. And so while the answer is definitely not here, it does allow us to speculate as to why that may be. Potentially operating at these higher concentrations is not a operating expense efficient point. So perhaps the cost to operate at these higher percentages is just not worth the value you may get from it. Could also be that there's just not enough competing technology at these higher concentrations to be able to have a competing bid for these water plants that are public bids type of systems. Another concern might be material compatibility. And we know at 10%, at 12%, what specific elastomers and steels will do, metals will do at these concentrations, but at 14, at 16, at 18%, do these same metals and elastomers hold up for the same lifespan? It's just not really known until we are able to put them in place and run them and see what we get as a result. Again, we have a limited data availability set. There might be more information available. Just have to fill in these data gaps. So the next item we wanted to take a look at was the ozone feed gas and what trends and impact into the industry that these have had. So if we look back, we can see here from 1990 to 2000, air-fed and oxygen-fed ozone systems were both prevalent, neither necessarily being more dominant than the other. However, in 2002, for whatever reason, oxygen just becomes the overwhelming dominant design choice, where you can see air-fed systems fall off, where they're getting an installation every couple of years. Oxygen has been the most prominent design for a feed gas. This is tracking LOX installations. We did look at VPSA and PSA and some of the other oxygen generating systems. There just wasn't enough installations for them to have uh, uh, a significant impact on the data. So LOX was by far the most significant. So we went ahead and just graphed that here. Now, if we take a look at the ozone dissolution method, we can see that the main dissolution method is fine bubble diffusion systems all the way up into the early 2000s. Side stream injection systems do have some starting in 1995. They do have some installations. They do start to become more consistent, so we're seeing them year after year in 2000 after 2003. But by 2011, side stream injection systems become the primary dissolution system. And so that's kind of interesting to note. So if we compare that with the transfer from air to oxygen, we kind of this overlay where as oxygen gained in prominence, side stream injection systems lagged behind it, but then also gained with it. One of the things we can take a look at then is what is the percent side stream needed to drive these systems, and it's less than 10% of the main flow on average is required to pull this gas in and drive it into solution. And in many cases, you can see the installations are less than 10%, 5%, 4%, with some higher cases, probably water reuse, maybe hydrogen sulfide injection systems, but the vast majority of the installations are below that 10% line. What that told us is this transition to oxygen, as compared to the dissolution method, did have an impact on the industry. That as that ozone feed gas transitioned to oxygen, the primary dissolution system changed to a side stream injection system. And we can conjecture as to why that is, but our thoughts are possibly that that higher ozone concentration presented a challenge to a fine bubble diffusion system. That lower gas volume made it difficult to design a fine bubble diffusion grid that gave you good coverage in the contactor, that would give good uniformity index going through the water, just as because less diffusers were needed because there was a lower gas volume to have to push into the water. However, that lower gas volume ends up being an advantage to the side stream injection system because there's less gas that has to be drawn in through a side stream injection system that allows it to have a smaller dissolution design, allows it to have a lower energy impact. And as we saw in the earlier slide with the needing less than 10%, many times 5% of the main line as a side stream to draw this lower gas volume now that's running at a higher concentration to the oxygen, drawing that into the system and dissolving it into the water system. So the next interesting thing that the data can provide us is showing us where is ozone currently being used. Map we can take a look at, and you know we have a pretty good coverage within the United States. And an interesting thing you can take a look at is if you follow the interstate system, that's pretty much where you're going to find the ozone systems right along in there, all along I-5 and Highway 99 there in California. I-5 traveling up to Oregon and into Washington. Florida is just completely covered there. And as you go up to the Atlantic seaboard there, you have good coverage. In the middle of the country, right there in Dallas, and working your way up through Oklahoma, again, pretty much following the interstate system, which makes sense because for the most part along the interstate system is where you're going to find the more densely populated cities, the larger metropolises, and so that's where you're going to have these water treatment plants. So of note, though, is the voids. So take a look at Alabama, Mississippi, really no ozone installations. Austin, San Antonio, Memphis, Louisville, places that do not have ozone that are actually still a fairly good sized city with a good sized population that are potential new application points for use of ozone. The other thing we can conjecture on this one would be if in these more sparsely populated areas, they are using ozone, but they are smaller systems and they're just not being captured by our data, or they're not using ozone just because they're not as familiar with them, or the ozone technology has not geared itself down to be able to handle these smaller type of systems. So some different possible avenues as to why that may be, something for further evaluation. Look at our neighbors to the north there. So Montreal, Toronto, definitely, lots of ozone installations in those areas. Windsor, Winnipeg, British, Vancouver and British Columbia definitely have installations. But again, we can identify a couple points there, and not to forget Newfoundland, with a couple of installations out there. But Edmonton, Calgary, some points of where there's might be opportunities for putting in ozone water treatment systems. Going forward, what we decided, we need to continue to collect data on our existing installations to backfill those data gaps. We really need to close those in for it to really tell us the whole story. In addition, we need to make sure that on future projects, we're getting all that data and filling it in so that we don't continue to have these gaps in data going forward, but we have a good, thorough, accurate data set that we can work from so that we can drive these analysis and correlation kind of projects. And we need to define what type of data format we want. What specific data do we want, and what format do we want it in? What units do we want it in? So it's consistent, and then we are able to do our analysis. And then we need to do a routine review and analysis of that data to make sure that it is correct in what we're looking for. I just wanted to acknowledge my references that I utilized in this presentation. And thank you for your time and any questions.